Suppose that triangle ABC is a right angled at B and has AB equal to n times n plus 1 and AC equal to n plus 1 times n plus 4, where n is a positive integer. Determine the number of positive integers n less than 100,000 for which the length of side BC is also an integer. Let's draw the diagram. We've got a right triangle. So let's say this is BC and this is A. So let's label it AB is n times n plus 1. And then the side AC, which is the hypotenuse in this case, is n plus 1 times n plus 4. Now, because it's a right angle triangle, we apply the Pythagorean theorem, and therefore that would be BC squared plus n times n plus 1 all squared would be equal to n plus 1 times n plus 4 squared. Just applying the Pythagorean theorem to that right triangle. Okay, so let's see what we can do here. Let's isolate for BC squared, put everything on one side. So this is going to be n plus 1 squared, n plus 4 squared, minus n squared times n plus 1 squared, like that. Okay, I think I can factor out an n plus 1 squared at least, and then that will leave me with n plus 4 all squared minus n squared, like that. And then the n plus 1 squared, I think I'll leave that alone for now. And then when you expand the stuff in the brackets and collect like terms, you just get 8n plus 16. All right, so what do I do now? BC squared, n plus 1 squared. I think I can factor out a 8 or a 4. I'm going to factor out a 4 actually, because 4 is 2 squared, and that is consistent with this perfect square. And when I factor out that 4, I am left with 2n plus 4. Okay, so now is where the discussion comes in. This is a perfect square, right? BC squared. This is a perfect square. It's n plus 1 squared. This is a perfect square. It's 2 squared. So in order for all this to be equal, this also has to be a perfect square. And therefore, that is the direction we are headed in now. We have to figure out how to make 2n plus 4 for a perfect square. Now, first of all, we are given some parameters. The parameter that we are given is that n has to be less than 100,000. So therefore, 2n would be less than 200,000. And then 2n plus 4, which is what we're interested in, would be less than 200,004. So, I guess now, obviously, we're not going to test out all the n's from 1 onward because that would take forever. But let's just see what we get. When n equals 1, 2n plus 4, I just want to get a somewhat of an idea here. 6 when n is 2, 8 when n is 3, 10 when n is 4, 12 when n is 5, 14 when n is 6, 16, which is the first time we get to a perfect square, by the way. So as you can see, when n is 6, we get a perfect square for 2n plus 4, and therefore this would work. So that's basically what we're chasing here. So that means, well, all the perfect squares, if we were to write them, would be 1 squared, 2 squared, 3 squared, 4 squared, dot, 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 all the way to something. Now, that something obviously has to be less than this. Yeah. So since 2n plus 4 has to be less than 200,004, that something has to be less than the square root of that. Yeah. And that is approximately 447.2. So we're going to go all the way to 447 squared. Yeah. But it's not that simple because we are only interested in even. Yeah. Because any number that is of the form 2n plus 4 will only be even. So we're only interested, for example, in 4 squared, since 4 is an even number. Or actually, 16 is an even number, I guess. Because there's perfect squares that are odd, right? Like 49 is odd, and so 49 is 7 squared. We can never get that with 2n plus 4. Okay, so let's think about this for a second before we calculate it. So there's 447 perfect squares total that would satisfy this guy. And then of those, we have to break it up into odd and even because we can only choose even. And if you're going from 1 to 447, there's going to be 223 even and 224 odd numbers from 1 to 447. But it's a little tricky here because if you notice that first as perfect score, we get a 16. So of these 223, we are not counting this guy. If you notice that, it starts at 6, so we'll never get a 4. So from the 223, we have to subtract 1 to get 222. And that is the answer to this question. Determine all real values of x for which this expression equals 4. Okay, so let's talk about this expression here. We're going to use a lot of log rules. And I'm assuming that you guys know all the log rules, so I won't go through each one. Okay, so here's this expression. And first, let's see what I can do to expand it. So let's here. This log x to the base 2, I'll leave alone for now. By using log rules, I can break that up into log 4 to the base 2 plus log x to the base 2, like that. And then, of course, don't forget that 1. And then plus, again, something similar, it seems like, log x to the base 2, but then using log rules, I can break that x over 64 into x to the base 2 minus x to the 64 to the base 2, I believe. And don't forget about that 9, and then all equals 4. Okay, so to make things a little bit easier, I am going to let log of x to the base 2 equal a, and then substitute that everywhere. So that's going to be a times a, oh, hold on here. Log 4 to the base 2 is just 2. Yeah, plus a, got to make sure I do this right, plus 1. And then this guy is a times a. 64 is what? 2 to the power of 6, right? So that's going to be minus 6, I believe. Plus 9, and then equals 4. So as you can see, it's a little bit cleaner. Okay, so let's expand all this. And when we do, we get a squared plus 2a plus 1. And this is going to be a squared minus 6a plus 9. A is equal to 4. Well, this one is very nice. It factors nicely, a plus 1. And this one is a minus 3, I believe. Squared, I should say. All right, great. So now, you might think, okay, well, don't those, it's a square and then the square root, so don't they disappear? Well, it would if it's greater than 0. See, if a is greater than 0, and then you have a squared and you take the square root, it would just be a. But if a is greater than or equal to 0, but if a is less than 0, and you have a squared over the square root sign like that, under the square root sign, it actually becomes negative a. So that's the, I guess, the not necessarily tricky part, but something that definitely needs to be looked at carefully. Okay, so let's, I guess we have a few scenarios, I think. Both positive, both negative. Yeah. We'll probably have 4 scenarios, I think. Both positive, both negative, one positive, one negative, and I'll walk through them. So the first scenario would be if a plus 1 is greater than 0, and a minus 3 is greater than 0. So that's the first one. Second scenario would be if they're both negative, so a plus 1 less than 0, a minus 3 less than 0. And then third and fourth scenario, we have a plus 1. Let's see here, a plus 1 less than 0, and a minus 3 greater than 0. And then the last one, a plus 1 greater than 0, and a minus 3 less than 0. Okay, so let's see what we get for each of these. So if a plus 1 is greater than 0, that means a is greater than negative 1, and then a would be greater than 3. So what that really means is that both of these are positive. So if we apply those to these, to that expression, it would basically mean a plus 1 plus a minus 3 is equal to 4. So that means 2a minus 2 is equal to 4. So 2a is equal to 6. So a is equal to 3. And if you recall, right here, log of x to the base 2 is a. So log of x to the base 2 is a. And since we have a equal to 3, this would be 2 to the power of 3 is x, so therefore x is equal to 8. Yeah, but remember, that's for an interval. It's for this scenario. Okay, we'll combine it at the end. So let me just go through each of these, and then we'll combine it all. Okay, so the next one, this guy here, this means a is less than -1 or a is less than 3. And then since they're both negative, this expression right here would be, applying this principle, would be negative. Let me think about this. They're both less than 0, right? Yeah, so negative a minus 1, and then negative a plus 3 is equal to 4. Yeah. So minus 2a would be equal to 2, I believe. So a is -1. So applying it to this guy, log of x to the base 2 is -1. So 2 to the -1 is x. So that basically means that x is a half. And again, it's for an interval. So we'll talk a little bit about that at the end. Okay, moving right along. So this is a is less than -1. A is greater than 3. Okay, this one I think has no solutions because a cannot be less than -1 and greater than 3. There's no common number. So this one I believe is a dud, meaning there's no solutions. Now let's see this one. A be greater than -1 and a is less than 3. Yeah, that is possible. Okay, let's apply it to this guy. So this will be a plus 1, and then this would be 3 minus a is equal to 4. So, this gives me 4 equals 4. Okay, so that doesn't lead to anything. All right, so let's combine them all. Okay, so when we combine them, okay, let's see here. I got to concentrate on these guys. What is the value of a? A is greater than -1. I think probably greater than or equal to. And then a is less than or equal to 3. Yeah. And for this, a is greater than or equal to -1, which is this scenario. X was 8. So x would have to be less than or equal to 8 in order for that inequality to hold true. And then for this a less than or equal to 3, x would have to be greater than or equal to -1/2. Oh, sorry. Is it -1/2? No, it's a +1/2. Sorry about that. Positive. Okay, so combining these, x looks like less than 8 or greater than 1/2, and that was for when the log of x to the base 2 was between, was it 3 and then -1, right? Yeah, going back and looking at our calculations, I believe this would be the interval that solves the question. At the Canadian eatery with multiple configurations, there are round tables around which chairs are placed. When a table has n chairs around it for some integer n greater than or equal to 3, the chairs are labeled 1, 2, 3, ... until n minus 1n in order around the table. A table is considered full if no more people can be seated without having two people sit in neighboring chairs. For example, when n is 6, full tables occur when people are seated in chairs labeled 1, 4, 2, 5, 3, 6, 1, 3, 5, or 2, 4, 6. Thus, there are 5 different full tables when n equals 6. Determine all ways in which people can be seated around a table with 8 chairs so that the table is full, in each case giving the labels on the chairs in which people are sitting. All right, so I guess this is one of those manual things. I don't think there's any specific formula. So we got 1, 2, 3, 4, 5, 6, 7, and 8. Okay. So we have to abide by a rule that we can't have anybody sit beside each other. Okay. So we have a few configurations. We start with 1, which is this guy, and then we can go 2 spaces next, which would be the 3, and then 2 spaces again, which would be the 5, and then 2 spaces again, which would be the 7. So like that, 2, 2, 2. Yeah, and then that's a configuration that would work. And then similarly, if we start with a 2, we can do a 2, a 4, a 6, and an 8. And these guys would satisfy the criteria that's listed in this stem. Okay, that's good. Now let's do another one. I think we've exhausted the 2, 2, 2, so I think now we're going to have to do 3s and 3s. So let's do a 3, 3. So we start with 1, then we're going to go 3. So instead of going to number 3, we're going to go to number 4, and then 3 again, so to number 7. And then, or you can start with 2 and do a 3, 3 jump, which would be 5 and 8. Or you can start with 3 and do a 3, 3 jump, would be giving us 3, 6, 1. Okay, the next one, I believe, would be a 3, 2. I think we can do that. So start with 1, we do a 3 jump, and then we do a 2 jump. And that's it. Similarly, you start with 2, and then you do a 3 jump, and then do a 2 jump. And then, or you can start with 3, and then do a 3, 2 to get 3, 6, 8. And then finally, I think the only one left is a 2, 3 jump. So we start with 1, and then we go jump 2 to 3, and then jump 3 to 6. Or you start with 2 and do the same kind of thing, you get 2, 4, 7. Or you start with 3 and do the same thing to get 3, 5, 8. Okay, so we got 11. But here's the thing. As always on math contest, double check, because we've overcounted. There's a double in here. Which one? This guy right here. That's a double. It's the same thing. So we got to subtract that one in order to get 10 unique cases for this question. A full table with 6k plus 5 chairs for some positive integer k has t people seated in its chairs. Determine in terms of k the number of possible values of t. So we are not given anything here. Okay, let's give an example then. Let's just work with an example. 6k plus 5 is the number of chairs, right? So let's just start with k equals 1, and that would make 6k plus 5 equal 11. And then let's just work with that for now, and then we'll try to extrapolate that. So let's put 11 chairs. Okay. Now let's see here. What are we going to do here? So has t people seated in its chairs. Determine in terms of k the number of possible values of t. Okay. Well, one scenario is you just jump 2. So 1, 3, 5, 7, 9. Yeah. If I put people at 1, 3, 5, 7, 9, that would satisfy. And then how many people did I put? Which is t, right? T people. So how many people did I put? Well, 1, 2, 3, 4, 5 people. And then how many gaps? Because gaps are going to be important. 4 gaps, right? Because there's 5 people, so there's... Well, hold on. Let me think about that for a second. Let me circle it. 1, 3, 5, 7, 9. How many gaps? 1, 2, we have a gap here, gap there, gap there, gap there, and this sort of big gap. So 5 gaps actually. Huh. Okay, it helps to kind of draw it out. Okay, what other scenario is there? Well, I think there's several, but let me just exhaust. All we're really interested in is the number of values of t. So it's kind of limited, regardless of what these scenarios are. If I make other scenarios, I can get the same value of t, but can I get another value of t? The maximum value of t, I believe, is 5. What's the minimum value of t? Minimum, if I do jumps of 3s, so 1 to 4, then 4 to 7, and then 7 to 10, that's the maximum I can jump, right? That gives me 4 values of t. Yeah, and then a number of gaps would also be 4. Okay, so since I only got 2 values of t, 2 values of t. So I just want to give you an example to kind of talk about what this question is asking. So if this question was saying, for k equal 1, what is the number of possible values of t? The answer would be 2. But they're not asking for k equals 1. They're asking in general for 6k plus 5. So then we have to sort of extrapolate our findings. Okay, so let's do that. Let's try to see if we can get a sort of a general solution to this question. Okay, so each gap, like if you look back at the diagram, has 1 or 2 empty chairs, right? Because, for example, look at this gap right here. It has 1 empty chair, and that empty chair was 8. But this gap over here has 2 empty chairs, and that was 11 and 10. So I think that's valid. So that means that you have either T or 2T empty chairs. Yeah. Because for each gap you have 1 or 2 empty chairs. Right, and the number of chairs is T. So this is valid. Now the total number of chairs is the number of people, the number of chairs with people and the number of empty chairs. So the number of chairs with people is T, and the number of empty chairs is either T or 2T. So the total number of chairs is either T plus T or T plus 2T. Or this represents the number of chairs with people, and this represents the number of chairs without people. So it's either 2T or 3T. Got it? So total chairs is between 3T and 2T, like that. And the total chairs is 6k plus 5, correct? Yeah, a full table with 6k plus 5 chairs. Okay, so that means 6k plus 5 goes here. So hopefully this will help. And then now let's solve for k in this inequality. And you guys know how to do that, I think. Let's see here. But let's do it one at a time because we're going to have to do a little bit of modification. Let's do this first, and then we'll do that second, or whatever. So if we have t 6k plus 5 is less than or equal to 3t, then that means 2k plus 5 over, dividing 3 by 3 is less than t. Now that means the t is an integer, so that means we can safely say that t is greater than 2k plus 2. Yeah. And then doing the other guy, it's 2t is less than or equal to 6k plus 5. And then let's see here. Divide through by 2, so t is less than 3k plus 5 over 2. And then I think it's safe to say that t would be less than or equal to 3k plus 2. Yeah, because t is an integer. Okay, so combining everything, we have t is less than or equal to 3k plus 2, but it's greater than or equal to 2k plus 2. So the total values, the total number of values that you can have for t, this is a little abstract. I'm going to give you an example. Let's say t was between 9 and 4. To get it, you just go 9 minus 4 plus 1, which in this case would be 6, right? So you're going to apply the same kind of theory or process there. So it'd be 3k plus 2 minus 2k plus 2 plus 1. And when you do that algebra, you get k plus 1. So there's k plus 1 possible values of t. And that completes part B. Determine the number of different full tables when n is 19. Okay. When n is 19. So, as before, 6k plus 5 is the number of chairs. But I don't know if that's helpful for us. All right, so let's see if we can get a pattern here. Let's make n, and then the number of full tables. Let's see what happens. Okay. When I think the lowest n, does it give us some parameters like where n starts? I think, yeah, n and this one right here, n has to be greater than or equal to 3. So it starts with 3. Okay. All right, so let's start with 3. When n is 3, we'll just define it as a function, f at n, and then hopefully we can get some sort of a pattern. Well, that's pretty straightforward. If you only have 3 chairs, the only way you can do this is if you have just one person at 1, or you can have one person at 2, or one person at 3. So there's only 3 ways of doing that. I just did that manually. F at 4, you can do it manually also. And this time, you got a table with 4 chairs. I think 1 and 3 or 2 and 4, I think, is the only way to get a full table according to the rules. So that would mean 2. And then F at 5, this one also manually. 1, 2, 3, 4, 5. Let's see here. 1 and 3, I believe. 2 and 4. 3 and 5. 4 and 1. And maybe 5 and 2. Is that a double? No, that's not a double. 5 and 2. Okay, so I got 5 there. Oh, I got into my my table there, but that's okay. We'll just put that there. Okay, keep going. F at 6, I believe we already have from the question, correct? Let's see here. Yeah, when n is 6, they already told me that the answer is 5. So that one we got. So that's 6 and 5. And then F at 8, I think we did that in part A. Yeah. And what did we get for part A? Somewhere it's, oh, here it is. We got 10. So F at 8 is 10. 7 we haven't done, but F at 8 is 10. I'll let you do 7. When you do 7 manually, it's actually 7. You just 1, 2, 3, 4, 5, 6, 7, like that, and then you count, just like I have done so far. Now you think, man, this is really time consuming. Well, it is, but hopefully you can look for a pattern, and this pattern is, to be honest, not that easy to figure out. I mean, once you see it, you think, oh yeah, it's obvious, but to figure it out on your own is a bit hard. And the pattern is such that f at n, if this is f at n right here, this column, is equal to f at n minus 2 plus f at n minus 3. So for example, f at 8 would be equal to f at 5 plus f at 6. So for example, f at 8 would be equal to f at 6 plus f at 5. So f at 6 was 5, and f at 5 was also 5. So f at 8 is 10, which it is indeed. And then you keep using that to just get other values. F at 9 would be 12, because it's going to be 5 plus 7. F at 10 is 17, and then you just kind of just keep doing that. And that's how you eventually extrapolate to, what do we want? 19. So 12, 13, 14, 15, 16, 17, 18, 19. And let me just fill in the numbers here. 29, 13 would be 39, 14 is 51, 68, 16 is 90, 17 is 119, 18 is 158, and then finally our 19 is 209. And 209 is the answer to this question. For every real number x, define x bracket to be equal to the greatest integer less than or equal to x. We call this the floor of x. For example, 4.2 floor is 4, 5.7 floor is 5, negative 3.4 floor is negative 4, positive 0.4 floor is 0, and the floor of 2 is 2. Determine the integer equal to, and so on. Okay, so we're concentrating on this guy right here. Okay, so let's concentrate on that. All right, so we have this expression 1 over 3 plus the floor of that plus the floors of all these guys, 2 over 3, 3 over 3, and so on, all the way until you get to 59 over 3. And finally, you'll get 260 over 3, like that. Okay, well, the floor of this guy is 0, 0, and then 1. Now, let me put in a few more to kind of illustrate. This would be 4 over 3, 5 over 3, 6 over 3. And hopefully, just putting in those will help. The floor of 4 over 3 will be 1. The floor of 5 over 3 will be 1. But once you get to 6 over 3, it'll be 2. So basically what will happen is you'll get 3 of each number all the way to the very end. Now, 59 over 3, that floor will be 19, I believe. Yeah. So you'll have 19, and the last one is 20. So you have 3 of everything until you get to 20, and then you'll have only 1 of those. So you can factor out the 3, and you'll have 1, 2, 3, all the way till 19, and then you'll have this one solo 20 at the end. And you guys know the formula for figuring out consecutive integers, right? If you go 1 plus 2 all the way to n, it's n times n plus 1 over 2. So apply that formula here, and you'll get 19 times 20 over 2 plus 20. So this looks like 190 times 3 plus 20, and that's 590. So that is the answer. Part B, determine a polynomial p at x so that every positive integer n m greater than 4, the floor of p at m would be equal to floor of 1 over 3 plus the floor of 2 over 3, and so on, all the way up to the floor of m minus 1 over 3. Okay, so let's see here. We are going to have to break this up into 3 categories, because the last term, which is this guy right here, will behave differently depending on if it's a multiple of 3 or not. So every number is either a multiple of 3, so every m could be like 3s, which is a multiple of 3, or it could be a multiple of 3 plus 1, or it could be a multiple of 3 plus 2. And then a multiple of 3 plus 3 would be just a multiple of 3. So we really don't have to go any further than that. And then let's see what happens. Okay, so let's plug in that here. So P at M for this guy, which is P at 3s. And let's see here, it'll be 1 over 3 plus 2 over 3, and then dot, 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 all the way till 3s minus 2 over 3 plus 3s minus 1 over 3, like that. Okay, so then we use pretty much the same kind of technique we did in the first one. And I believe, let's think about this for a second. So this is going to be 3 times 1 plus 2 dot, 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 all the way till, let's see here, I think s minus 1. Yeah, s minus 1. Right? Because let's say s was 10, that last expression would be 3 times 10 minus 1, which is 29. 29 divided by 3 would be 9. So yeah, s minus 1. Okay, so then using our formula, this would be 3 times s minus 1 times s minus 1 plus 1, which is s, all over 2. Yeah. I think that is it. Okay, so let's keep that for now. We'll use it later. Okay, using the same kind of methodology to do this guy, 3s plus 1. So this is 3s plus 1. So same thing, 1 over 3 plus 2 over 3, and then dot, 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 all the way till, then we got to put 3s plus 1 in these two guys to get an idea of what we're dealing with. And let's see, 3s plus 1, so it'd be 3s minus 1. Yeah, 3s minus 1 over 3. And the last one would be 3s plus 1, 3s plus 1 minus 1, so it'd be 3s. Like that. Okay, so this one looks to me like 3 times 1 plus 2 all the way till s minus 1, and then we're going to have a solo 3 at the end. Yeah. Kind of similar to part A, I guess, in some ways. All right, so using the formula, this is going to be 3 times s minus 1 times s over 2 plus 3. And then when you add that fraction, it will be, I'll let you add the fraction and simplify it. It's going to end up being s times 3s minus 1 over 2. Yeah, s times 3s minus 1 all over 2. Like that. All right. And then finally, P at M when M is equal to 3s plus 2 is 1 over 3 plus 2 over 3 dot, 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 and all the way. Okay, so we got to put 3s plus 2. So this is going to be 3s over s, and 3s plus 2 minus 1, so 3s plus 1. Like that. Okay, so this is going to be, I think, 1 plus 2 all the way till s minus 1. And then, let's see here. There's going to be 2 s's at the end. Hold on. Sorry. I think I might have made a mistake here. Sorry about that. This here is a 3, and this here, therefore, is an s. Yeah, sorry about that. And this is s 3s minus 1 over 2. So that is correct at the end. Yeah, my handwriting got a little messy there. Sorry about that. Okay, so this is actually s, and then we have another s. Okay, so then when you combine all these guys, we get 3 times s minus 1 times s over 2 plus this 2s. And then when you do all the algebra, you'll get a final answer of s times 3s plus 1 all over 2. Got it? So now we still haven't figured out the polynomial. We have to figure out some polynomial. They're saying determine a polynomial that satisfies these guys. And so for p at 3s, we've got this guy. And we're going to, instead of writing in that form, we're going to multiply top and bottom by 3. And when we do, we get 3s times 3s times 3s minus 3 all over 6. Like that. And then similarly, p at this guy, which is 3s plus 1, we're going to multiply top and bottom by 3, this guy, to get 3s minus 1 over 6. And then similarly, this guy, which is p at 3s plus 2, multiply top and bottom by 3, and we get 3s plus 1 over 6. Okay. So now, by some miracle, we have to come up with the polynomial that satisfies this. And I read the official solutions, and they came up with a polynomial out of nowhere. There's no actual methodology other than guessing. And that is this polynomial. And they're saying that that polynomial is going to work. Okay, great, but how did you know that, right? So that's the thing about this question. It's very, very challenging. And of course, you would expect it to be very challenging since it's number 10 on the grade 12 exam. Okay, well, let's see. Let's see what happens. We're going to have to substitute to see if it satisfies. So first, let's start with this scenario. P at 3 of s. And of course, this is our polynomial. So that's going to be 3s minus 1 times 3s minus 2 all over 6. And that, if you expand it all out, it becomes 9s squared minus 9s plus 2 over 6. And that it can factor to 9s times s minus 1. Let's see here. 9s squared minus 9s plus all over 6, and then plus, if you kick out the number, 1 over 3. But we have to now, of course, keep in mind that we have to take the floor of it. You see? You have to take the floor of it. So I think I didn't include that symbol throughout the question, but you guys understand that at the end we have to take the floor. So if we take the floor of this guy, so if we take P3 at s like that, then it's really the floor of this whole thing, 9s, s minus 1 over 6 plus 1/3. And when you do that, the 1/3 goes away and you just get 9s times s minus 1 over 6, like that. And when you expand this all out, or you can just factor out a, let's see here, you can rearrange this a little bit. You can put the 3s here and then put the 3 inside the bracket, and you get 3s minus 3 over 6. And you'll notice that it is exactly like this guy here. Yeah. So this polynomial holds true for the first guy. So now let's test it out for the second and third guys. So for the second guy, it would be P of 3s plus 1, right? And we put it in the polynomial. We have 3s plus 1 minus 1 times 3s plus 1 minus 2, and that's all over 6. And that's 3s times 3s minus 1 all over 6. And then we got to take the floor of this. So the floor of ps plus, sorry, p of 3s plus 1, very similar to the other one. You're going to have sort of this fraction sitting out there, and when you take the floor, that fraction will disappear. Or actually, I think in this one there is no fraction. Yeah, because if we just take the floor of that, it's just going to be 3s times 3s minus 1 over 6. And that's exactly the same as this guy. Yeah. Okay, great. All right, so we have to do the last one. So p3s plus 2 this time. That's going to be 3s plus 2 minus 1 times 3s plus 2 minus 2 all over 6. And that, let's see here, 3s plus 1 times 3s all over 6. And then, let's see here, is there any fraction sitting out? I don't think so. So when we take the floor of p3s plus 2, we will just get 3s times 3s plus 1 over 6, and this matches this guy up here. So if you can somehow miraculously come up with this polynomial and then show this stuff, you'll be able to prove the question.